the three voltage levels of transmission, of signal transmission. Whenever you have a question like that, you know then it has to be the multi-level binary techniques. They are the ones that adapt more than two signal levels, basically. That is from a positive, a level, to a negative. Okay, as compared to the numerator to zero, you only have either a positive or level. So just two signal levels, whereas the multi-level has got three, from a positive, level, and to a negative. Okay. When it comes to some of the issues that you might encounter within, like as I mentioned, just about every encoding technique has got some issues here and there. And with the multi-level binary is not an exception. Some of the issues that usually comes up with the multi-level binary technique is that synchronization with long runs of zeros and ones can be very, very impeding to the signal interpretation. And so usually when that happens, you can insert additional bits that forces transitions to give it the high and lows, or the positives or negatives required for that given transmission. To put this into perspective, let's go back to this. Assuming you had a long, let's say, right after the first two bits, you had 0, 1, and then the rest were all zeros. You're going to notice for the bipolar, it's going to be just a flat. And that could create synchronization problem at a clock and time clocking level within a given signal. So usually that's considered an issue within the signaling of a multi-level binary technique. And so usually when that happens, you have to introduce additional bits just to force the transition to take place, because it's what is expected within a multi-level binary schema or technique. And usually when that happens, then the signal gets scrambled properly to give you the right information that you need. If not, then you have a really bad data scrambling within your transmission. The other issue that comes up is with the multi-level binary is that's not as efficient as the numerator to zero, and especially when it comes to long-run synchronization of 1 to 0s. So it's not quite efficient in that sense, even though it was designed as an improvement on the numerator to zero. So each signal element only represents 1 bit, and receivers distinguish between 3 levels using a plus, a minus, or a 0. So those are the 3 states that you have within the multi-level binary techniques. A 3-level system could usually be represented with a log base 3, which is 1.5 bits. So the 0.5 is usually what's identified. 1.58 is what is very considered an inefficiency within a given signal transmission. It's like saying that a signal or a bit sequence can have half of that. If you look at the various bits that we have, they're either 0 or 1. There's no 0.5 in it. You get it? So if you introduce in 3-level signal levels, that could really confuse signals that have been transmitted. But it's part of the issues that comes up within the multi-level binary techniques that we have. Okay, so hence one of the reasons why it's not as efficient as the numerator to zero, where it's either going to be a 1 or a 0, not a half signal. sorry, half bit or whatever, And they also require approximately 3 decibels more signal power. So power-wise, when it comes to its DC, direct current uh, application or drawing of power, it's always one more. So you're looking at a high power usage for a given transmission when you're adapting the multi-level. So power transmission is very high on this, and since we don't really want to be using up too much voltages uh, for transmission, because keep in mind the byproduct of high voltage or high electrical signal is what? Heat. So you don't want devices to generate too much heat. So we try to use the minimum, the less signal power for most of our electronic devices as much as possible. If you start adapting, if you're basically incorporating a lot more of signal power or a lot more voltages just to power a particular signal or transmit a given data signal, and you can have serious issue with the devices with heating. So now we're moving on to the fourth grouping, which is the biphase. The biphase technique uses two other techniques: the Manchester encoding and differential Manchester. This is actually the most widely used techniques for data transmission. It's very very efficient um, in terms of signal synchronization at the clocking level. Very efficient. So able to identify errors and even uh, 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 mitigate some of these errors within transmission because of how it's structured. Okay, so let's look at it a bit. Let's look at it so we can easily identify some of these. Transition in the middle of each bit. That's one key thing that you will notice within Manchester encoding or the biphase techniques. For the Manchester encoding, you notice signal actually transitions in the middle of the various bits, and there's a reason why that is done. Midway transition serves as a clock. Exactly. So this is the reason why they do serve as a clock, clocking or synchronization of the transmission with reference to data being passed through a medium. And they usually use low to high transitions represented by ones. High to low transitions are represented by zeros, and widely adapted within data communication systems like the IEEE 802.3, which is the physical and data link layer of MAC addressing, especially at switching levels. This is a highly adaptive encoding technique, very, very efficient. Like for instance, when your information is coming out of your devices at the physical level of the OSI model, where we need to make sure that information that we basically carried from the application level maintain its form and its integrity as it's about to leave the device onto a transmission medium. We need to make sure that they have the right information. If there are going to be any problems or errors or any issues to impede the transmission integrity, then we need some key uh, uh, information embedded into it to address that. And like I said, with uh, the mid transitions, all of these help address some of those issues that might come up. So once again, clocking is quite essential. Error detections, congestions, all of these that impedes signal transmissions are well addressed within the biphase technique. I mean, like as usual, even though it's quite efficient at the data communication level or just data transmission level, it also does have some issues as well to it. So it's not like it's perfect, but at least it guarantees better transmission as compared to the other two, from Norton to zero or the multi-level binary techniques. So the other one is the differential Manchester encoding. And with differential Manchester encoding, we have, as once again, we do have the mid bit transitions, mostly used for clocking. Okay, transitions at the start of a bit period, and they're usually represented by a zero with a zero. There are no transition at the start of a bit period that's represented a one. Application-wise, the token ring topology within LANs is one of the implementations that is adapted. So let's look at some of the schematics or the graphing of some of these techniques within the biphase, or at least we can understand the importance of mid-bit transitions and how they play a key role in helping us with signal clocking and signal synchronization. So as we mentioned it within the Manchester, a zero bit is represented by a high voltage signal. A 1 bit is a level voltage signal, and transitions usually takes place from 0 to 0. So when you move from 0 to 0, you transition with high voltage pulses at the start, and 1 to 1 for level voltage, level signal voltage at the start. And all transitions are alternated mid bits. So let's look at this. For instance, with the Manchester, you have the high, and keep in mind, like I said, within the biphase, there are always transitions mid bits. Every single one has got a transition at the mid bits, or transitions only occur at mid bits. Okay. So with zero, we had a zero transition. Sorry, we have a zero voltage as a high voltage pulse. And if you look at the next bit, it happens to be a 1. So it means that we have to make sure that when we're moving to that 1, we start from a low voltage point. And the only way to achieve that with mid-bit transitions is by making sure that from a high, we drop down mid-bit to a low, and then maintain a low start for the 1. And then for 0, the only way to maintain the high is to keep it at the particular state of the transition, the mid-bit of a given bit sequence, to address the various high or low voltage pulses for the given bit sequence that you have. So high transition, we have a 1, so we need to start from a level or a low voltage pulse. The next bit is a 0, we need to start from what? A high. The next bit is a 0. So, and the only way to achieve that, since voltage 0, so your bit 0 has to have a high voltage start, is by making sure that we transition and move upwards to the start of the bit to give it that high voltage start. Okay? And the same applies if you look at it very carefully with the 1 to 1. A 1 must have a low start, transition mid bit. Now the next bit is a 1. So it has to have a low start. The only way to achieve that is if we drop down back to a low voltage start before we transition. So I hope you're catching on to some of these things. Okay. So just keep this in mind. Don't be confused or anything. Low zeros start from a high voltage pulse, and all bit sequence must transition mid-bit. Just keep that in mind with the biphase. It must transition mid-bits. So with that in mind, and knowing that uh, 0 has to start from a high and 1 has to start from a low, and you basically be able to figure out how to manipulate the signal graphing to address some of these highs and lows and the transitions within mid-bits. Okay? With Manchester, zeros are high voltage starts, ones are low voltage starts. We need uh, uh, we need no transitions within the various states that we have. We just make sure that to address a given bit state, we have to make sure that we follow its normality, its voltage level sequence to address its highs and lows. As we did for 0, if you note, all zeros have got high, 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 and all ones have got lows, 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 and lows. They all have the low stats, and zeros have got the high stats. That's the differential, which gets a bit interesting because of uh, the transitions that we have, especially the 0 to 0 with high voltage starts, and 1 equals a high or low voltage signal with no transitions. So if you notice, the ones they are alternating. So you have the first one that we have at a high, but you notice the other one at a low. Another one has got a high. The next one has a low, a high. So it's just it can get a bit tricky, but I guarantee if you start working it out with various bit sequence, you start getting to understand the way the encoding techniques is really applied within the signal transmission. Okay, challenges or pros and cons that you might find with the biphase techniques. You have synchronization on mid-bit transitions. At a pro level, helps with self-clocking because of timing. Hence, one of the reasons why it's very, very efficient in LAN transmissions, up to 10 megabits per second. Has no DC components, so we don't have to worry about signal fluctuations and knowing how to adjust and mitigate some of those. So error detections are very, very effective when you do have a technique that incorporates MIDI transitions and have got alternations and non-alternations within its various encoding schemes. Very, very effective in LANs up to 10 megabits per second. So hence one of the reasons why it's much widely adapted on most transmission level at the physical and data link level of the OSI model. That guarantees signal validity, I guess. The cons are at least one transition per bit time, and sometimes you may have two in the process, and that could pose a problem. Maximum modulation rate is always twice the non-return to zero, and they also require a lot more bandwidth. It's in a way it's a good thing, but if you wanted to adopt in a much more simplified, non-high bandwidth implementation uh, like uh, like terminals and other devices, other communication devices, it would be too cumbersome for that. The frequency needs to be higher, and that cannot meet the requirements of that particular device or terminal's needs. Okay, so some terminals need just low bandwidth to operate. So if you try to adapt to any of the biphase techniques, you could create uh, issues. So those are the cons that you'd be looking at. Well, I wouldn't necessarily say it's that much of a con, because if you're applying it within the right application, then there wouldn't be a con over here in terms of the more bandwidth then. Okay? But data transmission wise, it's good. You need the high bandwidth so we can be able to transmit high capacity data across a given medium, and also be able to adjust to error detections and self-clocking at the synchronization level. Another thing that will be a very, very a con or a disadvantage about biphase technique is that it's less effective at long distance transmission, which actually doesn't make sense. Imagine if you had to have this, if you had a long distance transmission over various miles or kilometers, and you had to repeat some of these mid-bit transitions for a given information, you will notice that it could create uh, a lot of overwhelming overloads on that given transmission line over that uh, uh, distance duration or distance length or signal duration. So hence we say it's less effective. And especially if you do have interferences within the signal transmission over a longer distance, it doesn't become very, very practical anymore. Okay, so that's a summary of all the four groupings that we have from the for the first three groupings. The last one, which is a sampling, um, so the scrambling techniques, the scrambling techniques are quite interesting in their implementation. Very, very has a specific needs in so to speak in its implementation, and they usually adapted uh, by various regions for key specific uh, applications. Although although the biphase techniques have achieved widespread, like you said, within most data transmission needs or most local area network applications at relatively high data rates up to 10 megabits per second. They've also not been widely used in long distance applications. So we need to figure out a different technique that can address the long distance application needs, and that's where the scrolling techniques comes into play. The principal reason um, for the scrambling technique is to address high signaling rates in relative terms to the data rate that goes with it. And also sort out inefficiency that relates to the cost within long distance applications. So if we wanted to address some of those issues that falls within the first three groupings, then you need to adapt something like these scrambling techniques. Um, so the two main techniques that you'd find within the scrambling techniques for long distance transmission services are the bipolar with 8-0 substitutions. So the first one is bipolar with 8-0 substitutions that you have, and the coding scheme is usually based on the standardized bipolar AMI implementation and that the multi-level binary techniques. So you still have you can have a 3-level signaling voltage levels that you have within the bipolar or the multi-level binary encoding scheme. So in other words, the scrambling techniques adapt a bit of the multi-levels, especially the bipolar AMI as its scheme of encoding signals for a given transmission. The other one, if I'm not mistaken, is the high density bipolar using 3 zeros encoding. As I mentioned earlier on, the bipolar is usually adopted within the US regions. Within the US regions, or the North American region uses the bipolar with 8-0 substitutions. And then the encoding schemes that's commonly used within the European and the Japanese market is the other version of Scrambler, which is the high density bipolar 3 zeros encoding. Okay, and I don't want to go into this as complicated as it is. I don't really want to go in depth into it. But if you were to go back to its illustration, usually the scrambling technique uses scrambling to replace sequence that would produce constant voltages. These filling sequence must produce enough transition to help with synchronization for clocking, for sub-clocking, and also be able to recognize receivers and replace with original sequence bits that is needed to fulfill the various sequence that is produced at a constant voltage level. Okay. Signals also, or the sequence also must have the same length as the originals. And like I say, if you look at signals in general, it's not that easy to have to maintain the same signal length all the time. Since we deal with electronic devices, is you're bound to encounter some challenges within the signal fluctuation, really within voltage transmission or voltage fluctuation. Sorry. So if you look at that in terms of that, you would have to be able to fill in some of these sequences to address that. So hence the reason why the multi-level binary is adapted within this, so we can address issues that relate to voltage fluctuations that could come up within systems. Okay, since we need to have the same signal length, then ideally we need to figure out a way to make sure that's maintained within a given transmission that we have.